Today, we're going to pull back the curtain on something we use every single second of every day, but almost never think about: electricity. We're going to follow the entire trail, starting from a humble piece of rock, and see how it ends up as the light in the room you're in right now.
It's such a simple little thing, right? A flick of the wrist. But what you're actually doing is kicking off a colossal industrial ballet of intense heat, incredible pressure, and mind-boggling engineering, all happening in perfect sync just for you.
For a huge number of power plants, that journey begins deep in the earth with coal. You can think of it as a battery, basically, packed with sunlight stored millions of years ago. Its nickname, black gold, isn't just for show. It hints at the incredible energy that's just waiting to be unlocked inside. So, how do we get that energy out? Well, we have to do something humans have been doing since the dawn of time, but on a scale that's almost impossible to imagine. We have to build a fire. This right here is the absolute key to the whole process: combustion. It's the chemical reaction that cracks open the coal and lets the energy out. But we're not just talking about burning something in a fireplace. Oh no. This is a super controlled, highly engineered process designed to squeeze out every single last drop of heat. To get that kind of perfect, hyper-efficient fire, engineers live by what they call the 3 Ts. First, you need enough time for the fuel to burn completely. You need the perfect temperature, hot enough to ignite everything, but not so hot that you create nasty byproducts. And finally, you need turbulence, a violent, chaotic mixing of the coal dust and air to make sure every last particle finds an oxygen molecule. You get those 3 just right, and you have an absolute inferno. Okay, so we've created this unbelievably hot fire. Now, all that heat has a job to do. Its entire mission is to take something as simple as water and turn it into an unstoppable force of nature. That fire is roaring inside the furnace, which is lined with a massive, winding maze of tubes, all filled with pure water. This whole structure is the boiler, and you've got to think of it like the world's most intense pressure cooker. It's using immense pressure to create something way, way more powerful than just regular old steam. And here's a little detail that shows you just how precise this whole operation is. Inside that boiler, they don't use pipes. They use tubes. Now, you might think, what's the difference? Well, a pipe is just for moving stuff from point A to point B. A tube, on the other hand, is a high-precision piece of equipment measured by its exact outside diameter, built to handle insane stress and transfer heat perfectly. It's a tiny distinction that matters a whole lot. So here's where the pressure cooker idea really pays off. At sea level, we all know water boils at 100 degrees Celsius. But look at this. Inside that boiler, at 50 times the pressure of the air around us, water doesn't boil until it hits 264 degrees. By putting it under all that pressure, you can cram way more energy into the water before it finally turns into steam. And it doesn't even stop there. That steam then gets blasted with even more heat in a process called superheating until it reaches an absolutely staggering temperature, often over 650 degrees Celsius. We're not talking about the wet, foggy steam from a kettle anymore. This is a dry, totally invisible, high-energy gas that is just itching to do some serious work. All right, so we've taken the chemical energy in coal and turned it into thermal energy in this superheated steam. That's a huge step. But the next trick is the big one. How do you turn all that heat and pressure into actual movement? Well, that happens in the absolute mechanical heart of the power plant, the turbine. Honestly, that's the simplest way to think about it. A steam turbine is basically a gigantic, incredibly complex, high-tech pinwheel. All of that superheated, high-pressure steam we just made is blasted through nozzles and aimed at a series of perfectly shaped blades, forcing a massive rotor to spin at thousands of revolutions per minute. And there are 2 main ways engineers get this to happen. The first is an impulse turbine. This works exactly like that pinwheel we talked about. A powerful jet of steam just smacks into the blade and pushes it. But the other kind is a reaction turbine, which is much more like an airplane wing. The steam glides over the blade's curved surface, creating a pressure difference that generates a force, pushing the blade and making it spin. Most big modern turbines actually use a clever combination of both ideas to be as efficient as possible. So we've done it. We've turned heat into incredibly fast rotation. We are so close. Now it's time for the final magical transformation, turning all of that spinning mechanical energy into the electricity that powers our lives.
That spinning turbine is connected by a thick shaft directly to a generator. And inside that generator, you have massive coils of copper wires spinning inside a super powerful magnetic field. And that motion, a conductor moving through a magnetic field, gets the electrons in the copper excited and flowing. That flow, that is an electric current. It's a fundamental principle of physics, and it's the foundation of pretty much all the power we use.
Now here's a really cool piece of trivia for you. A generator this big creates an enormous amount of waste heat. Early models were just cooled by blowing air over them, but modern ones, they're filled with pure hydrogen gas. Why? Well, it turns out hydrogen is 7 times better at transferring heat away than there is. It lets engineers build generators that are way more powerful without them getting physically bigger, making the whole design more compact and efficient. We've made the power. The journey is almost complete. But that massive fire we started with, it left some stuff behind. So what happens to all the byproducts? The reality of combustion is that it creates waste, mostly exhaust gases and millions of tiny, fine particles of ash. You can't just pump all of that stuff straight into the atmosphere. So the final leg of our journey is all about capturing and managing that waste. And one of the cleverest bits of tech they use for this is the electrostatic precipitator. Just think about rubbing a balloon on your hair and sticking it to the wall. It's the exact same idea. As the exhaust gas or flue gas flows past, all the little ash particles are zapped with a negative charge. Then, they pass by these huge metal plates that have a positive charge. And, just like a magnet, the negatively charged ash sticks to the positive plates. Every so often, the plates get a good shake, and all the collected ash just falls down into a big container. So what's left of that cleaned gas goes up a chimney to be dispersed high up in the atmosphere. And the scale of these chimneys is just wild. The tallest one in the world, over in Kazakhstan, is almost 420 meters tall. That's taller than the Empire State Building. But what about all that ash they collected? It doesn't just get buried in a landfill. Turns out this fly ash is actually a really valuable material. It's a key ingredient in making stronger, more durable concrete. They use it to build up road embankments. It's even used to make bricks. It's a fantastic example of industrial recycling, turning a waste product into something useful. So there you have it, from a chunk of coal dug out of the ground to the light in your room. It's this incredible chain of violent, controlled transformations of energy, all of it happening constantly, silently, in the background to deliver the power we depend on. This process has powered our world for more than a century. It really makes you wonder, doesn't it? What new journey will power the light switch of tomorrow?